Hello, my name is Jesus.escobar.cerezo and I'm a medical physicist at the Hospital Clínico Universitario San Cecilio in Granada, Spain. I'm going to talk about the Diagnostic Reference Levels classification tool with Python. Diagnostic reference levels give us information about the usual radiation dose delivered in diagnostic procedures, depending on the body part examined. These levels may be local, regional, or national, and are represented by the third quartile of the dose distribution for a body part location and image modality. If we use a dose manager, we can export data from specific devices to perform our studies. These programs allow us to select different parameters from diagnostic image. We are interested in body part examined and those parameters as CTDI, DPA, or MNGT. Traditionally, we work with the data in a spreadsheet, filter the results, and perform a statistical analysis to find the median dose value that characterizes certain modality in a specific body part location. The workflow is as follows. We read and store the data in a Pandas data frame. Then we filter the data, delete non-clinical procedures, classify by age, delete invalid entries, and remove the less abundant protocols. Then we group the protocols by body location. This is usually the most difficult part because the protocols' names vary easily. The data are then analyzed and stored. This is the decision dictionary where we program the variables that will be used in the program. In general, these are keywords to perform a wise filtering process. Then, a classification dictionary will group the protocols by location and diagnostic modality, using again some keywords. These lists are in constant growth as the program performance is tested. Then a selection of the desired output parameters is set. Now we are going to follow the program workflow. First, data duplicates are dropped, as some dose managers receive same information from several sources. Then a specific device is selected, assuming we are analyzing a list of several devices. The data are then stored in a Pandas data frame, and some key parameters are stored as the main dose parameter, which defines which kind of modality must be used: CT, conventional radiology, or mammography. Then the filtering process begins. First, we fill empty cells with not a number value to remove them easily later. Then we drop those studies without those information. In the next step, we remove non-clinical studies as topograms or scouts, studies with a value of pitch equal to 0 in CT scans, for example, age, and less abundant protocols. The variables defined previously in the master dictionary are used in this step. Then we reach the most important part of the program. Here, the location classifier stores the protocol in the correct body part. To do this, the Levenstein distance concept is used. It compares two words and computes the relative distance between them. The distance accounts for the number of changes necessary to transform a word into the other. In this way, we can compare words to look for the closest one in a list of terms that characterize certain location, as could be ear, eye, face, or skull to refer to the head. In the master dictionary, we can see some of the terms that we have included in each location to classify the protocols. These lists are in continued growth. Once all the protocols have been grouped, we will study each location to extract the statistical information desired. In this analysis, a Gaussian filter is applied to remove outliers. Other procedures to delete these may be applied, but we have found that this action does not affect especially the results. Finally, the results are written in an Excel row. The program detects if there is an existing Excel file. The file contains or not a row with the device of interest and acts in consequence, creating a new one or overwriting the existing one. In the master dictionary, we can customize the output information from the data frame that we want to store.